Hi students, Miss Gardner here. So let's get to this video reviewing periodic trends. So far we have already seen that the periodic table, when organized in order of increasing atomic number, leads to a lot of repeating trends. We've seen this already when we draw Bohr models, and we can see that the number of valence electrons repeats across or down groups. So for instance, if you look at everything in group 1A, hydrogen, lithium, sodium, those all have one valence electron. Beryllium and magnesium and everything in group 2A have two valence electrons, right? And so on and so forth. So that is just one of the many trends that are repeated periodically on the periodic table. So let's get into a couple more today. All right. While we are going through this, I highly recommend that you have a periodic table out in front of you so you can see the relative location of the elements that I'm talking about. So make sure you've got one of those handy. All right, it's also important to have a basic definition or understanding of effective nuclear charge, because that will dictate a lot of the things I'm about to talk about. So the effective nuclear charge is the actual amount of positive charge experienced by an electron in an atom. All right, so we know that the positive charges are in the nucleus, the protons are in there, and the electrons are outside surrounding the nucleus in the orbitals. All right, so those two things are attracted to each other. But as you get a larger and larger and larger atom and you add more orbitals and more electrons, the outer electrons also feel a little bit of repulsion from those other electrons. That's called electron shielding, where other electrons are kind of blocking that positive charge from the outside electron, and they're also giving some repulsive forces. All right, so just keep that in mind as we add more orbitals in between the nucleus and the outer electrons, what kind of feel they're getting from the positively charged nucleus. All right, the first periodic trend we're going to talk about is atomic radius, and that is half the distance between the nuclei of two atoms in a chemical bond. All right, so if the distance between the nuclei is represented here by d, the radius is half of that. All right, same thing as radius in a circle, if you have ever seen that before in geometry. So half of the distance across that circle. So generally here, we're going to be talking about this in terms of size of the atom. All right, so let's talk about this. How does atomic radius change when we go left to right across a period? So atomic radius decreases from left to right across a period. If you look at period 2, lithium, beryllium, boron, etc., you can see represented here that the lithium atom is the largest out of the whole period. All right, that might sound a little counterintuitive because neon has more mass than lithium. Neon has 10 protons, it has more neutrons and electrons than lithium, so why is it so much smaller? All right, and this is because everything in period 2, they all have 2 orbitals in their Bohr model. But as we go left to right, we're adding more protons to the nucleus. All right, so the protons in the nucleus, they're getting stronger. They're pulling stronger on those outer electrons. All right, so as that pull gets stronger, the atom itself shrinks. All right, they're being pulled in tighter, and you can think of it almost as being a little bit more dense. All right, they're being held closer and more tightly by the nucleus. Now, if we go down a group from the top of the periodic table to the bottom, atomic radius increases. All right, this might be a little bit more straightforward. And this is because as we go down a period, we add an orbital, we add an energy level. All right, and so that distances those valence electrons from the nucleus and puts them further away. And then they're also just held on less tightly by the positively charged nucleus because of all those other electrons that are in between. So potassium here is much larger than lithium. All right, if you want to visualize this across the whole periodic table, here's a little snapshot. You can see helium is the smallest element in this view, and cesium is the largest element. All right, the second trend we're going to talk about is ionization energy. That is the energy required to remove an electron from an atom. All right, so if we have lithium here, that means how much energy is required to take this one valence electron away, to turn lithium into an ion. All right, so let's compare, again, going left to right across a period. Ionization energy increases going from left to right. So compare these two atoms in period 2. We have lithium and we have neon. All right, I showed their relative size here as well. So neon is smaller than lithium, and that is because it has the stronger positive charges or more positive charges in the nucleus that's pulling those electrons in tighter. All right, so as it does that, those valence electrons are held more tightly by the neon nucleus than the lithium nucleus. All right, so as we go from left to right, ionization energy increases. It becomes harder and harder to pluck one of those valence electrons away. It takes lots of energy to yank one away from neon. The opposite is true if you go down a group. So ionization energy decreases from top to bottom on the periodic table. That is because as atoms are getting bigger, those outer electrons feel the nucleus's attractive force less. All right, they're further away and they're shielded by other electrons. So it doesn't take very much energy to pluck one of those outer electrons away. So it would be easier to remove this valence electron from potassium than from lithium. All right, if you want to see this with some numbers here, this is ionization energy in kilojoules per mole. All right, so the darker purple means higher ionization energy. So it is highest in this upper right corner with helium and neon and fluorine, and it is lower down here near francium and cesium. All right, if you look closely, you'll notice this trend doesn't perfectly go along with the way that I explain this to you. And some of that has to do with more of the quantum mechanical model of the atom and where are those electrons in those quantum orbitals. But for what we're going to talk about here, you can see this as just higher and upper right and lower left. All right, the last trend we're going to talk about is electronegativity, which is the ability of an atom to attract electrons when it is in a bond. So a bond is just a shared pair of electrons, a covalent bond. So in this cartoon here, we have chlorine and hydrogen, and they are sharing this pair of electrons. But you can see chlorine is pulling those electrons closer to itself. It's being a little more greedy. All right, that's because chlorine is more electronegative than hydrogen. It's attracting those electrons towards itself more strongly. All right, just like ionization energy, electronegativity increases from left to right. So if we compare lithium and fluorine, fluorine is more electronegative. All right, it's also because fluorine is smaller. Since all those valence electrons are being pulled in tighter by the nucleus is closer to the surface, it's felt a little bit more on the outside, and it can attract those electrons more strongly. All right, electronegativity decreases as you go down a group, and this also has to do with how the size changes. So as we get bigger and bigger and bigger, the nucleus of, say, potassium, it's buried under all those other energy levels, and that valence electron, it's way out there, if we're talking about attraction on that. And other electrons are shielding the positive charge. So the positively charged nucleus just can't attract electrons very strongly. All right, now there's one exception to this rule here. So noble gases are not considered electronegative. So in ionization energy, they have the highest ionization energy in their periods. But they're considered to have zero electronegativity. And that's because they have their filled outer shells. They have full valence shells with 8 electrons. All right, and because of this, they're very energetically stable. And so they don't attract any more electrons. They don't want to give up any electrons, but they don't want to attract any more. All right, so they have no assigned electronegativity values. And for my class, you can assume and consider them to have 0 electronegativity. Right. Also, we talk about noble gases not being involved in bonding very frequently, and this is why. All right, so here is a table of electronegativity values. These do not have units. And here you can see fluorine has the highest electronegativity value, 3.98, and francium down here is the lowest. All right, so our noble gases, they are lacking any numbers at all, so you can just ignore them. And fluorine is our most electronegative. All right, let's do a couple practice problems. And I recommend that you write these down on a piece of paper and pause the video to do this practice. All right, first up, atomic radius. Which of these elements has a smaller atomic radius? All right, do this for each pair, and then you can check your answers at the end of the video. All right, next set of practice problems, ionization energy. Which element in each pair has a higher ionization energy? Go ahead and pause, get your answers, and then check at the end. All right, and last, which of these elements has a higher electronegativity value? And remember, noble gases, consider them to have 0 electronegativity. All right, check your answers for numbers 1 through 12 here. And if you have any questions, go back and review in the video or come see me in office hours. All right, and with that, you should now be able to define atomic radius, ionization energy, and electronegativity. You should be able to explain the pattern of each of the periodic trends going across a period from left to right or down a group. You are now also able to explain why the trends are what they are using terms like the effective nuclear charge and attraction and repulsion. All right, and you should also be able to rank elements based on their size, ionization energy, or electronegativity given a periodic table. All right, review any notes that you have, do some practice problems, and ask me questions if you have them.